This is another example for a static force analysis. So this differs from the earlier examples we saw here. So in this mechanism, you can see there are two forces which are acting. So we have two forces, F1 and F2, which are acting, and an input torque. Whereas in the earlier examples we saw either there is a torque and a force or a number of forces. Whereas in this case it is two forces and a torque. So to solve this, we will be applying a principle of called as the principle of superposition, where we analyze by separating the forces. So initially we assume that only force F1 is acting. We neglect the force F2, and later we neglect F1 and we consider only the force F2. And then finally we add up the values. You will be seeing them in a moment. So let us neglect the force F2 acting on point E. And before that, so based on the given data, we know we have to draw this diagram, draw this sketch, and the angle is given 60 degree, that is for AB, and the force F is acting at point E such that DE is 25 and DC is given as 35. In other words, EC will be 10 mm. So a force F1 is acting on link DC, that is the fourth link, so that it acts at the it is given as if it is acting at point E, that is 25 mm. So DE is 25 mm. So F1 is known both in magnitude and as well as direction, whereas F2 is known only by its magnitude, and the direction is also known, that will be exactly parallel to on this link. That is parallel to the ground level. So assume that this is fixed to a ground at link A and D, and this is parallel. So F2 and F1 both are known in magnitude and as well as in direction. Now we'll apply the principle of superposition. Let us neglect the force F2 and draw a free body diagram. So separate link DC, similar to the previous examples which we saw in part 2 of static force analysis. So separate this link DC and draw F1, that is from point E, extend the line. So this is the line of action of force F1, and draw CO parallel to this link BC, so that they meet at point O, and then complete or join DO, which represents the line of action of force F14. So I repeat again, draw DC parallel to this link, in other words, it's a free body diagram of link 4, and then mark E, and then extend from E to O, such that this represents the line of action of force F1, that is exactly at 60 degree as per the given data, 60 degree from the ground level. And then so based on this diagram, you have to draw a force polygon, and then so that this is F1, so F1 is given as 20 newtons. You can assume that 1 centimeter is equal to say 5 newtons. If that is assumed, then it will be around 4 centimeter. And draw BC, not B, that is extend BC and draw just a parallel line parallel to this BC, link BC, and then from here F14, then extend this line such that they meet at point C. So this F14 will be parallel to this line F14, and this F34 will be parallel to this line of action of F34. Thus we will be able to determine the magnitude of F34 and F14, similar to the previous examples which we saw in part 2 and part 1 videos. Thus F14 is found, F34 is found, and then separate link 2, there is AB, and the line of action of that is in this case, so this will be F32 and this will be F12. That is what is given here. So this represents F32 and this represents F12. Thus based on this we'll be able to find out what is the input torque, that is T1, neglecting the force F2. So we have neglected force F2 and we found out the torque value when only one force acts. So this is what is given here. For equilibrium, F12 is equal to parallel and opposite to F32, and also F34 is equal to minus F43 equal to F23 equal to minus F32, which is equal to minus 17.6 newtons, because they are equal in magnitude but opposite in direction. So substitute this value in here, you will be getting a positive value for the torque T1. So when you say torque T1, we are finding the torque T1 by neglecting F2. Okay, now what we will do now is, let us neglect F1 now. So F1 must be neglected. We assume that only F2 is acting. So it is acting exactly at point E. Now similarly draw what you call this is a free body diagram of link PEC, and this is F2. This F2 is parallel to this. So draw F2, that is OE, so that it this is link that is OE represents the line of action of F2. Now CO, extend this line CO here, so that they meet at point O. So EO and OC. This CO represents the line of action of force F43. Now from here, it is at point B, join B with O. Join B with O, and this represents the line of action of force F23. So let me repeat again. You're drawing a free body diagram of this link 3. Now F2, let's just draw F2 parallel to this, draw F2, extend this, and then extend this line here, extend so that they meet at point O. So join this EO represents the line of action of F2, and this CO represents the line of action of F43. So this is third link, this is F43, line of action of force F43. Now from link B, extend this line so that it meets at point O, and this represents the line of action of F23. Now from here, based on this, draw a force polygon similar to the earlier one. So this C dash A dash represents F2. Since F2 is given as 25 newtons, again assume 1 centimeter is equal to 5 newtons, so this will be around 5 centimeter. And similar to the earlier ones, draw say F23. This F23 will be parallel to this line of action of F23. So draw this, and then F43 we know. Draw using a mini drafter, draw parallel to this line of action of F43 so that they meet at B dash, and thus we will be able to find the magnitude of F23 and as well as F43. And similarly separate the link AB and then F32 and F12. So this is F32 and then F32. So this line F12 will be parallel to line of action of F32. And then similar to the earlier examples which we saw, determine the height, and then the product of F32 into H will be the torque T2. That is when force F2 alone acts by neglecting F1. And thus this is the thus it was found out around 438 Newton mm. So the total torque will be T1 plus T2. That is this T1 and this is T2. This is T2. So the total torque will be 700 Newton mm. Now we will see about what we mean by a D'Alembert's principle. The D'Alembert's principle states that the inertia forces and couples and the external forces and torques on a body together give static equilibrium. So the inertia force F1 Fi is given by Fi is equal to minus m into Fg, where Fg is the acceleration of the center of mass of the body and m is the mass of the body. And inertia couple is given by minus Ig into alpha, where Ig represents the moment of inertia about an axis passing through the center of mass of G, center of mass G, and then and perpendicular to the plane of rotation of the body, and alpha represents the angular acceleration of the body. You can also give even explain the D'Alembert's principle by another something like an equation, that is sigma f plus fi is equal to 0, sigma t plus ci is equal to 0. That is the total summation of the total torque and the inertia couple must be equal to 0, and the vector sum of forces and the inertia forces must be equal to 0. Or in other words, the D'Alembert's principle, the vector sum of forces is the vector sum of forces and the torques. So this is the torque and this is the couple, it must be equal to 0. So you call this a D'Alembert's principle. And the dynamic analysis of a slider crank mechanism. In this case, we spoke about the dynamic analysis. In dynamic analysis, the inertia forces are considered, and inertia forces are due to the mass of the components as well as its acceleration. Now this particular module on dynamic force analysis consists of a number of formulas for it to memorize. I have so many formulas, like I have to memorize what is the velocity of the piston, the velocity of the acceleration of the piston, and then angular velocity and the angular acceleration of the connecting rod. So this is the formula. This is the formula: sin beta is equal to sin theta by n. And these are all based on simple derivation based on this diagram. So this is the initial position of the slider, and this is the final position of the slider when it moves, and this r is the radius of the crank, or is the length of the crank, you can say. This is that of the connecting rod. This is the angle beta that makes with the line. This line is called the line of stroke. This is the inner dead center, this is the outer dead center. We have a number of formulas for you to memorize. I think wherever I have mentioned as formula, we will be using it for our problems. We have so many formulas. I think I have identified around 17 formulas which I have given to you during the class hours. And you have some simple problems which are totally based on formulas. You have a horizontal gas engine running at 210 rpm. It has a bore of 220 mm and a stroke of 440 mm. See, all the given data may be substituted in the formulas, and you will be able to determine what is the turning moment of the crankshaft, thrust on the bearings, acceleration of the flywheel, totally based on formulas. I think if you go through these problems, it will be very, very self-explanatory. I don't need to elaborate further. So the accelerating torque, turning moment minus resisting torque. So all these things are formulas. So based on the given data, after substitute the values, you will be able to find the results. It's a very anybody can understand even if you go through it, because basically it is based on formulas. The data will be given, substitute the data, determine the results. That's all. Okay, thanks for watching. We'll see you again.